All right, it's 9:40, so we're going to start. If you're here in person or at home, please take a couple minutes to try the warm-up problem, and then we'll talk it over. All right, would anybody like a little bit more time to work? All right. So the problem is asking us about this radio selling company. So they sell physical radios, and they produce them quite cheaply, and they sell them quite cheaply for $7 and $13 respectively. And we're supposed to find the cost, revenue, and profit functions for the company, assuming that they're linear for a given year. Okay, so we're not going to attach a variable to this office space and supplies cost. We're going to consider that our fixed cost. So who can tell me, or who can take a guess at what our cost function is going to be? It's going to be some function which depends on Q. We'll call it C of Q, where Q is the quantity of radios sold. Yeah, Ryan?
12,000 plus 7Q.
Perfect. Okay, so the costs to the company are $12,000 that year for their office space and supplies, plus $7 for each radio that they make, meaning that if Q is the number of radios that I make, then I multiply that by 7 to get the amount of dollars that I need to spend on the supplies to make the radio. Okay. Now, let me ask a more general question. Who can tell me what the difference is between revenue and profit? Yeah, Sam?
So profit is revenue minus cost.
Exactly. Profit is going to be pi of Q. That's going to be equal to our revenue minus our cost. Okay, that's exactly right, which means that revenue is really kind of representing the amount of money that we are bringing in, right? Now, if I want to calculate how much money I made, I need to think about how much money did I bring in, how much money did I lose, find the difference between those two things, and that'll give me my profit. Okay, so profit is kind of like a net change, whereas like revenue is going to be the net or gross income. Okay, so for our revenue function, that's going to be all the money that's coming in. And it looks like our only source of income is that we're selling each radio for $13. So that's going to be 13Q. So if I want to find pi of Q, I'm just going to subtract these two functions. R of Q comes first, that's 13Q minus, and I'm going to put in parentheses, 12,000 plus 7Q. Okay, I use the parentheses because I want to make sure I distribute that negative sign there. So we get 6Q minus 12,000. Okay, running out of space here. All right, the last part of the problem asks us, what is their break-even point? What does break-even point mean for the profit function? Yeah.
It's where profit is equal to 0.
Yeah, profit should be equal to 0. That's the break-even point. That's when I have covered all of my costs with revenue. Okay, if my revenue is exactly equal to my costs, then I have basically the same amount of money that I started with. Okay, so if we want to find the break-even point, I'm just going to take this profit function here and set it equal to 0 and solve. Okay, so we'll do a little bit of algebra and we'll get Q is equal to 2,000. And we could be a little bit more specific than that. We could say 2,000 radios. That's how many radios we should make in order to break even. All right, pretty standard problem. One thing that I noticed on the exam was there were a lot of people who, when they were computing the cost function, there was like a cost of beer per gallon or something like that. A lot of people computed the cost function as a constant. But the cost function should be a linear function which depends on the quantity of goods produced. Okay, so that's why we have this Q here. So it's very important that we attach this variable here for our cost function. We want to make sure that it depends on the quantity of goods produced. Okay. Any questions about the warm-up problem? Okay, well, the warm-up problem is kind of leading us into what we're doing today. We're going to talk about section 2.5, which is all about marginal cost and marginal revenue. And you may be thinking, we already talked about marginal cost and marginal revenue, and that's true, we did. We talked about marginal cost and marginal revenue for linear cost and revenue functions. We said that if we have a linear cost or linear revenue function, then the marginal cost or the marginal revenue is just the slope of that line. Okay? The slope or the rate of change of that line. And now we're going to get a little bit more complicated. We're going to look at cost and revenue functions that look like this. Maybe they're a little bit curvy or wacky or crazy. Okay, so we're going to expand our understanding of what marginal cost and revenue mean in terms of cost and revenue functions that may not be straight lines. Okay? And based on what we've learned so far in Chapter 2, you may be thinking that the generalization of marginal revenue, which would be the rate of change of a linear function, the generalization to a nonlinear function is going to be based on the instantaneous rate of change or the derivative. Okay, so that's where we're going. So let's have some definitions here. I don't have an extra box today, so I'm going to have to make an extra page. And this is where we're going to do our definitions. All right. So, marginal cost. Sometimes we abbreviate this MC. Equals C prime of Q. And we can approximate it by C of Q plus 1 minus C of Q. Okay? And the reason that we can approximate it by this is this looks kind of like, by this I mean this red thing here, looks kind of like the rise part from our rise over run, okay? And if we were to consider it as a slope, well, our inputs here would be Q plus 1 and Q. So we're taking the outputs and subtracting them on the top, and on the bottom we would have Q plus 1 minus Q, which would just be 1. So usually when we have a fraction over 1, we just don't write the denominator, because we know if we divide something by 1, we just get back what we originally had. So we're not going to worry about this denominator. But I want you guys to see the connection here, that this thing here highlighted in red is like the slope of the direct path between the points Q comma C of Q and Q plus 1 comma C of Q plus 1. Okay? That's what that is. All right, and marginal revenue. Sometimes we call it MR. It's going to be the same thing except with the revenue function. It's R of Q, and it is approximately equal to R of Q plus 1 minus R of Q. Okay? Very important that we have these little squiggly equal signs. That means approximately equal to. Okay? It's not going to be exact. And well, they don't put this in the book, but I'm going to put it here. Marginal profit. Maybe we'll abbreviate it MP. Is R prime of Q minus C prime of Q. And you can approximate it in much the same kind of way. You plug in Q plus 1 and then plug in Q and subtract those two numbers, and you'll get something which is relatively close to the real marginal profit, provided that your profit function is nice and smooth. But for now, don't worry about how smooth your profit function. I will always give you nice, smooth functions for cost and revenue. Okay, so we've just expanded our understanding of marginal cost to cover a larger class of cost functions. That's all we've done. Okay, so let's go up and do problem number 1. Okay, so if it costs Office Min $15.65 to produce 950 notebooks and $18.40 to produce 1,050 notebooks, approximately what is the marginal cost at a production level of 1,000 notebooks? Okay. I'm going to try to digest what this word problem is really asking me for. Okay? What this problem is really asking me for. It says, okay, we have two data points on a graph. 950, 1565, and 1050, 1840. We have 2 points on our graph, and we're asked to estimate what we think the slope of the function is halfway in between those 2 points. So if I was to draw what's going on here, it would look like something like this. Here's 950, and here's 1050. We have some points here. 950, it's 1565. 1050, it's a little bit higher than that. It's at 1840. And this is 1565. Okay, so this is the information that we're given in the problem. We have just 2 data points. What they want us to do is estimate at this red point here. Presumably there's some kind of data point. We don't really know where it is. But we want to know what's the slope of the function at that data point. Okay. This could also be rephrased as saying find the slope of the tangent line to the graph of f at that data point. Okay? But the complicating factor is we don't actually know what our function looks like. Okay, we're dealing with a cost function here. So let me draw in some possibilities. Okay? We might have something which looks something like this. Or maybe our cost function looks something like this. And in both of these cases, we're going to have a different tangent line slope. That one maybe looks like that. And this one, who knows, maybe it looks more like that. Okay? So these the straight pink line has a slope which is equal to the instantaneous rate of change of the pink curve at that point, and the green line has slope equal to the derivative of the green function at that point. And you can see that they're slightly different. But what we're going to do here is say that since we know that we have these 2 data points here, which are in blue, which got a little bit covered up, we have these 2 data points here, we know it has to pass through those 2 points. And so our estimation is going to say, well, if we take the slope of the path which goes through these 2 points, it will be not too different from the slope of the green line or the pink line. That is the intuition that's going on here. Okay, we did a little bit of this when we talked about instantaneous rate of change for the first time. We can estimate it if we have kind of data nearby. Okay, so the way I'm going to estimate it is just by calculating the slope of this red line. Well, this red line goes through the 2 points, 950, 1565, and 1050, 1840. So the way I'm going to calculate the slope of that line is the same way that we calculate the slope of every single line that we've done so far in this class. We'll do 1850 minus, oh, sorry, that should be 1840. 1840 minus 1565, all divided by 1050 minus 950 equals, what, 275, I think, over 100 equals 2.75. Okay, so if I was going to answer this question in words, I would say the marginal cost is approximately $2.75 per notebook. All right, so a little bit of approximation going on here. I think the intuition behind this problem is maybe a little bit more challenging than we're used to so far. Okay, and in general, for the rest of the class, we're kind of starting to get into the calculus part of the class. There is going to be a little bit of a spike in difficulty. I just want you guys to be prepared for that. But as always, you have a ton of resources that can help you out. You can come to my office hours. You can go to Aaron's SI meetings, MTC, all that sort of thing. Or just send me an email. I will help you figure out how to get on track. Are there any questions about problem 1? Okay, doesn't seem like there's any questions. So let's try problem number 2 together. So let's have everybody try part A and part B on their own. I'll give you guys a couple minutes and then we'll reconvene as a group. Would anyone like a little more time on part B? Did anybody find part B challenging? I think part B is a little bit tough in terms of interpretation. I think some people found it a little bit tough. All right. Who wants to help me with part A? How do we express marginal revenue in terms of our units based on this word problem? Yeah, Michael?
Would be dollars per toy.
Yeah, exactly. It's just going to be dollars per toy. So we could write it like this. Yeah. So marginal cost, marginal revenue, marginal profit is always going to be in terms of dollars per unit, basically. In our case, the unit that's being produced is one cat toy. Okay? All right. Part B, I think, has a lot more meat on it. Somebody want to take a crack at it? Yeah, Michael again?
I said how much money was being made at 10 toys sold.
How much money was being made at 10 toys sold? You're very close. That's going to correspond to the actual revenue. Remember, revenue, so revenue is like, let me write it in a different way. The way I'll write it is, R of Q represents, amount of money coming in when selling Q units. In our case, that means Q toys. So the marginal revenue, remember this is R prime of Q, is going to describe how revenue is changing. Okay, how revenue is changing. Did you have a question, Derica? Okay. So the way that we're going to write this down is, and it's a little bit convoluted of a concept, the way I'm going to write it is increasing the number of toys sold from 10 increases revenue at a rate of $4 per toy. Okay, so getting a little bit complicated on this interpretation here. Let's have a graph to see what's really going on here. If I were to draw my revenue function, here's 10. Maybe it looks something like this. In terms of this graph, which this is the graph of R of Q, can somebody help me determine what is the meaning in terms of the graph for the marginal revenue to be equal to 4 when Q is equal to 10? So I want to add something onto my graph here and say, what is the meaning of this 4 here, my marginal revenue being 4? Yes, Ellie?
Is that like at the production level of 10, the slope is 4?
Yes, that's exactly right. In other words, the slope at this point, I always do that. The slope at this point, which remember we call the slope of a curve at a given point, we say that that is, what we're really referring to is the slope of the tangent line to the curve at that point. The meaning of MR equals 4 is exactly to say that the slope of this red line is 4. Okay? Which is a description not of the revenue, but rather of how revenue is changing. Okay? what it's really saying is that if we increase the amount of toys that we sell from 10, we're going to be increasing the amount of revenue that we're earning at this rate, approximately. So, at different points, the marginal revenue might be different, right? If we're producing 100 cat toys, maybe our marginal revenue is negative. If our marginal revenue would be negative, then producing more toys would somehow magically result in less revenue. That would be bad. I think it's more likely you'd see a situation like that happening with profit. But this is telling us how revenue is changing. If we think that increasing the amount of toys we produce will increase revenue, then maybe it's a good idea to produce more toys. So having this information about the way that the graph is changing is telling us a lot about maybe what we, not so much about what financial situation we are in, but rather how changing some of the parameters in our business is going to affect our financial situation. That's what's happening with this marginal cost and marginal revenue stuff. Okay, I think B is a pretty tricky question for the first time that you're seeing this concept. Are there any questions about A or B? 2A or 2B? All right. Let's go on to problem number 3. We're going to do problem number 3 together. Okay, so a bit more graphical intuition. So this graph here shows the cost and revenue functions for some company, and Q is measured in thousands of items, and price here is measured in thousands of dollars. And we have these 3 levels of production, okay? We can either produce 500 items, 1,500 items, 2,500 items. And we're supposed to use the information that's in the graph, which, visually speaking, we can see the values of the cost and revenue function. And visually speaking, we can also kind of see the marginal cost and marginal revenue by looking at how quickly these graphs are going up. You know, later on, this blue graph is going up at a slower rate than at the start. So that's telling us that at the start here, we had pretty high marginal revenue, and later on, our marginal revenue was smaller. Oh, that wasn't what I wanted to push. Oh man, now I can't delete that. Guess I'll erase. Okay. All right, so for each production level, state whether the company is making or losing money and whether or not the company should increase or decrease production in order to increase profit. Let's start by answering the question, is the company making money? Making or losing money? For each of these 3 points. So, part A, 500 items. Okay, if my Q here is measured in thousands of items, 500 items means Q equals what number? What should Q be for producing 500 items? And Q measures the number of items that we're producing in thousands. Yeah, it should be 0.5. Okay, so I'm going to go to this x value right here, and I'm going to kind of trace it up, and I'm going to look at the value of the cost function compared to the value of the revenue function. Which one is larger?
Revenue.
Yeah, revenue is larger at this point. What does that tell us about profit?
They're making money.
Yeah, we're making money. Profit, remember, is the function that we get when we take the revenue function minus the cost function. So if I were to take the height of the blue line and subtract from that the height of the red line, I would get a positive number because the height of the red line is smaller than the height of the blue line. So I'll do it in green since we're earning money. This distance here is going to be our profit. Okay, so we are making money. Okay, 1,500 items. That tells us that Q is equal to 1.5. I'm going to go to 1.5, go up. Looks like, again, the blue line is higher, so I'm going to put a little green line here to represent the fact that we are making money. The difference, the distance of that green line, if we were to measure it over here on the side, that distance would be the amount of profit that we're making. Okay, so again, making money. All right, now 2,500 items. Okay, we'll go right here. We look up. Now it seems like our cost function is much higher than our revenue function. That means that we're losing money. Okay? Our cost to produce that many items is very high. The amount of money that we can make from selling them is relatively low. Therefore, we're losing money. And this distance here, this red line, let me highlight it with red just to make it extra clear. The distance of this red line here is representing the amount of money which we would lose if we produced 2,500 items. Okay, so we're losing money. Okay, so the second part of the problem is to say, should the company increase or decrease production in order to increase profit? That's what we always want to do, right? We always want to increase profit. Okay, so this is a question about marginal profit. If our marginal profit is a positive number, then that means increase in production corresponds to increase in profit. That would be great. If our marginal profit is a negative number, then that means increasing production decreases profit. We don't want that. So, in terms of this graph, we don't have a profit function drawn in here. We have a cost function and a revenue function. But we know, remember, that pi prime of Q, that's the marginal profit, is equal to R prime of Q minus C prime of Q. So if we want to know, the question mark here is it greater than 0? That's what we'd really like to be able to say. If I have a difference of two things, it's going to be greater than 0 when the first number is larger than the thing that we're subtracting. So really what we're trying to answer here in terms of whether or not marginal profit is positive, it's exactly to say at the given x value, is the slope of the blue curve greater than the slope of the red curve? If so, we're in good shape. And moving forward, the distance between those two graphs is going to increase. If I have one line that's growing at a certain slope, and I have another line that's growing at a smaller slope, then as I move forward, this distance between them is going to get larger. Okay? So we could answer this question in terms of looking at the slopes of the blue and the red curves and just trying to guess, okay, it looks like the blue slope is a little bit bigger. We can also just look right at the graph and say, look, if I move this green line, my pencil is too big. If I move this green line in this direction, do we think it's going to get taller or shorter? Taller, right? Taller green line means bigger money, right? That's what we want. So if I could also consider just look at the tangent lines. At this point, it looks like we're going up fairly steadily. And at this point, we're going up slightly less so. Okay, this is telling us that the marginal revenue is larger than the marginal cost. The marginal profit is given by the difference between these two things. So if I take a smaller number and I subtract it from a bigger number, I'm still going to have a positive number. Okay, I think I've beaten this into the ground at this point. The green line is getting bigger. We like big green lines. So we should, let me go back to my other size. We should increase production, because doing so is going to make our green line get bigger. Okay, now let's go to 1.5. Q equals 1.5. Now I'm concerned with this region here. As I move to the right, is my green line getting bigger or smaller? Yeah, it's getting smaller. So, should I increase production or not? No, we like big green lines. We should not increase. Production. Okay, part C, 2,500 items. So now I'm concerned with this region here. Okay. Should I increase production? Why not? The line is going to get bigger if I move to the right.
You're not making money because the cost is higher than the revenue.
Yeah, if my line gets bigger, that's a problem because my line is red. Red line bigger means more loss. Okay, it's just like Star Wars. We like the green guys. We don't like the red guys. Okay. So we should not increase production. Okay, there was a lot of graphical intuition there, and I kind of flip-flopped a little bit partway through on whether we were talking about things algebraically, whether we were talking about things in terms of slopes of tangent lines, versus whether we were talking about differences in revenue and cost. Kind of a lot to unpack in this problem. So let me give you a couple seconds to think if you have any questions about this problem. It was a doozy. No questions? Let me get some thumbs. Thumbs up means perfectly clear. Thumbs down means not so clear. What are we thinking? Some side thumbs, some up. Okay. Thank you for that feedback. Yeah, I think you will get used to these problems in the same way that you get used to every math problem by practicing. Okay. So we'll do one more problem. Use the given cost function to answer the following questions. Okay. Supposed to estimate the marginal cost for Q of 5, or for Q equal to 5, and interpret what this means practically. Okay. So we're interpreting a marginal cost again. So our minds should be going back to this problem where we interpreted the marginal revenue right here, where we were talking about how what that means is that increasing production from that point will increase cost or revenue by a certain amount. Okay? Or at a certain rate, I should say. So we're doing the same thing here. We want to estimate the marginal cost for Q equals to 5. I know that the marginal cost is equal to the derivative. Okay? So this is going to be equal to C prime of 5. C prime of 5 is going to be the slope of the tangent line when Q is equal to 5. So this is my point here. This tangent line looks like this. And I want to estimate the slope of that line. Well, it looks like we went over 5 and up 50. So the rise was 50, the run was 5. I'm going to say 50 over 5. C prime of Q is approximately 50 over 5, which is equal to 10. Okay, the units that I would give, well, it doesn't look like we have units. Let's say that this is dollars, and this is units. I would call it dollars per unit. So what does this mean practically? In terms of my actual business model, the fact that my marginal cost is positive means increasing production from 5 units increases my cost at a rate of $10 per unit. Okay, that's what's going on. So let me use a different color for the second part of the problem. Increasing production from 5 units. From 5 units. Come on. Increases cost at a rate of $10 per unit. Okay. So remember, when we're talking about marginal cost now, we have to be specific about where we're talking about marginal cost. Previously, we had questions that would ask, what is the marginal cost? With no specification of where. That's because for a linear function, the rate of change is constant everywhere. However, now that we have these curvy functions, we now need to specify where we are checking the marginal cost, right? It's just like when we did the instantaneous rate of change, or the derivative, right? The slope of a curve, we have to say, well, where exactly do you mean? Because the slope is changing all over the place. Okay, so the place here is encoded in this part which says from 5 units, increasing production from 5 units. That means we start at 5 and we increase from there. That's telling me to go to this point right here, okay, on the graph. Increases cost at a rate of $10 per unit means that increasing from that point is going to increase our cost. Okay, I'll do B really fast and then we'll be done. I'll do B and C. It'll take me like 30 seconds. All right, is the marginal cost greater at Q equals 10 or Q equals 35? All right, well, that's pretty easy to answer. We just look at the slope of the tangent line at this point versus the slope of the tangent line at 35. And we're just going to compare which one looks like it's bigger. I think Q equals 35 has a greater slope. At approximately what production level is marginal cost 0? That's asking when is C prime equal to 0? That's going to be when the slope of my tangent line is exactly horizontal. Happens at this point here, Q equals 20. Okay. That's it for today. If you have questions, stick around after, or I have office hours today from 12 to 1.